Section 5.3, the fundamental theorem of calculus. It is in this section that we give a precise inverse relationship between the derivative and the integral. First, we need to describe functions of this form, g of x equal to the integral from a to x of f of t dt, where f is a continuous function on the interval a, b, and x varies between a and b. If x is a fixed number, then since g depends on x, the integral will be a definite number. However, if we let x vary, the number represented by the integral varies, and this defines a function of x, which this is what we have called g of x. If f is a positive function, then what g of x represents is the area so far from a to b. Here's a visual example. So in this picture, f is the curve that is in front of you. A is 0 and b is 4. So here we have x is between 0 and 4, and then our function is just y equal f of t is the curve. So now just using this picture to understand this function that we have described, let's just find a couple of things. So first let's find g of 0, which would be the integral of the function f of t from 0 to 0. This is just 0 from what we saw in the previous section. G of 1 would be the integral from 0 to 1 of the function f of t dt, which is really just the area under the curve from x equals 0 to x equals 1. And if we take a look at this picture, this is just a triangle. So that would be 1/2 times base, which is 1 unit, times height. And you can see that this goes up to 2 units. So this just ends up being 1/2 times base, which is 1, times height, which is 2. That just becomes 1. Okay, so then g of 2, that would be the integral from 0 to 2 of the function f of t dt, which just means now we are continuing all the way to 2 units, and we would like the area now that's under the curve. But notice this is not just this rectangle that I'm shading. It's also the piece that we already found between 0 and 1. So this becomes the 1 unit that we had as the area from 0 to 1, plus the area that is now from 1 to 2. And this is just a rectangle with a base of 1 unit from x equal 1 to x equal 2, and then a height of 2 units. So that becomes 1 times 2. So that becomes 1 plus 2, which is 3. So as you can see, as the x values are changing, 0, 1, 2, so are the values of these integrals. They are changing as well. Let's find g of 3, which means the area all the way from 0 to 3 that is underneath that curve f of t. We already have some of it. We already have the triangle and the rectangle. That's 3. So we know we're just going to add to that. The area that we're going to add is just what would be under this part. And this has some curvature to it. It looks like we've taken up a little more than a half of what's maybe in the rectangle that could be represented like this. So if we say something a little bit more than a half, we can just estimate. How about we say 2/3? So I'm just approximating here. There's no deep calculation that's going on. So this just gives me an area so far of 3 2/3. And then finally, if I wanted to find, keeping this going to the right, g of 4, that would be the area from 0 to 4. But now you can see that we're introducing a negative area because that's below the x-axis. And this somewhat has the same shape as what was above the x-axis between 2 and 3, So it looks like maybe we're subtracting. So we had 3 2/3 from before, but now we're subtracting something that looks the same. So we've now reduced our area because, again, we had some negative area that was below the x-axis. All right, so that's really all that this function does. It's just adding to the area as we are increasing the value of x from the beginning, 0, to the end, 4. So now let's be more specific. Given f of t equal to t and a equal to 0, show that g of x, which by our definition of these type of functions is equal to 0, the integral from 0 to x of f of t dt, we would like to show that that's equal to x squared over 2. So this integral here, 0 to x of f of t dt, we're saying that we're given that f of t is just the function t. So this is the integral from 0 to x of t dt. The function f of t equal to t is a line with slope 1. And at t equal to 0, it crosses the y-axis. That's the y-intercept of that function. So if we draw a little picture for this, I've just got a line with slope 1. Then at some point x, wherever this is, the y value is the same. Right? On the y-axis, if I move any units along the x-axis, the function f of t equal to t just takes me back to the same value. So in fact, actually, the horizontal axis is the t-axis. So this coordinate right here would just be x comma x. So if we want to think what is the area underneath that curve, again, we just have a triangle. The horizontal side is x units long. The vertical side is x units long. So the area is equal to 1/2 x times x, which is 1/2 x squared, which is x squared over 2. Exactly what we wanted to show. So with this one specific example, notice how the result of this area is very similar to the antiderivative of f of t equal to t. If we were to find the antiderivative back in section 4.9, we would take t, that has a power of 1, we would increase that power to t squared, but then we have to divide by that new power, that's t squared over 2, which is very similar to x squared over 2. So this example is an example of a general version that we call the fundamental theorem of calculus. And here we're going to start with part 1. In this whole section, we're going to get 2 parts. The fundamental theorem of calculus part 1 is something that we just saw in this example. So here's what that part says. If f is continuous on the interval ab, then the function g, defined by g of x equal to the integral from a to x of f of t dt, where x is between a and b, if that function is continuous on ab and differentiable on ab, then g prime of x, the derivative of g, is equal to f of x. And we're going to walk through a proof of this. So we want to show that a function that we've defined is differentiable. So we start with that, and we start with a difference quotient. So remember, part of the derivative, all the way back in chapter 2, is this difference quotient, which would be g of x plus h minus g of x divided by h. By the definition that we have for the g function, g of x plus h becomes the integral from a to x plus h of the function f of t dt, and then minus g of x. Here I'm just replacing exactly what we said g of x was in our difference quotient. And then that's all divided by h. By properties of integrals, this limit x plus h, I'm going to play around with that a little bit. I can split that first integral up into 2 integrals. it becomes the integral from a to x of f of t dt plus picking up at x the integral from x to x plus h of f of t dt, and then minus the integral that we already had at the end, the integral from a to x of f of t dt. We can see here that we've got the same integral, but with opposite signs, so they cancel each other out. And what we're left with in our difference quotient is the integral from x to x plus h of f of t dt divided by h. For the sake of this proof, we're going to assume that h is positive, but this would work the same way if h was negative. Since f was assumed to be continuous on the closed interval a, b, then it is continuous on the closed interval x to x plus h, because that is a smaller interval between a and b. Thus, by the extreme value theorem, there are numbers u and v in that small interval x to x plus h, such that f of u is equal to m and f of v is equal to capital M, where lowercase m and capital M represent the absolute min and max, respectively, of the function f on the closed interval x to x plus h. So that's an old fact, but now we're going to take advantage of that fact. So at this point, let's use one of the properties that we saw in just the previous section. If f of t is bounded by two constants, so lowercase m is the minimum, that's less than or equal to f of t, which is less than or equal to capital M, which is the maximum, for values of t that are between x and x plus h, what we saw is that gave a restriction on the integral. This relates to lowercase m times the difference of the limits of integration, so x plus h minus x, that is less than or equal to the integral from x to x plus h of f of t dt. And that is less than or equal to capital M, the maximum, times the difference of the limits of integration, x plus h minus x. So we've got this integral is now bounded by two constants. We can simplify, obviously, because the x's will cancel, and that tells us our integral is bounded by those constants. So now we can relate this back to our difference quotient. Our difference quotient is then in the following inequality. So notice all I did was just take where we left off, and then I divided by h everywhere. And when I do that, now we can see that our difference quotient is bounded by two values, lowercase m as a minimum and uppercase m as a maximum. If you can kind of see where we're going, we used some facts about the extreme value theorem and then also a property of integrals, and it looks like as we're about to take a limit, the squeeze theorem is going to come up. So since f of u is equal to m, lowercase m, and f of v is equal to capital M, then I can just substitute for those, and I have f of u is less than or equal to our difference quotient is less than or equal to f of v. So now let's let h approach 0. So we're taking the limit as h approaches 0 of everything that I have here. So if h is approaching 0, then that means that x plus h approaches just x. Since we had u and v between x and x plus h, if x plus h is heading towards x, what do you think happens to u and v? They also have to approach x. Everybody's getting pushed down to x. So that means u approaches x and v approaches x, which then, as h approaches 0, that forces f of u to approach f of x and f of v to approach f of x. By the squeeze theorem, as h approaches 0, the difference quotient approaches f of x. If this is going towards f of x and f of v is going towards f of x, then what's in the middle also has to approach f of x. So what did we just show? We just showed that g prime of x, which is by definition equal to the limit as h approaches 0 of g of x plus h minus g of x divided by h, which is equal to, as we simplified, the limit as h approaches 0 of the integral from x to x plus h of f of t dt divided by h, that approaches f of x. So we just showed that g prime of x is equal to f of x. Notice in that whole conversation, we also showed that we have a differentiable and then therefore continuous function. So that proves the first part of the fundamental theorem of calculus. Now, you aren't going to be required to replicate this proof, but you should see how we strung together a bunch of facts that we've been collecting all semester. This is why this becomes a culmination of a lot of things that we've learned this semester. So let's take a look at a couple of examples. First, find the derivative of the function g of x, which is equal to the integral from 0 to x of the square root of 1 plus t squared dt. So if you compare this to the fundamental theorem of calculus part 1, we've got the same sort of format. It's just that a is equal to 0. And it doesn't matter what a is equal to. You'll notice that the derivative doesn't really bother with that. So the derivative of this function, we can just note that f of t is equal to the square root of 1 plus t squared. By the fundamental theorem of calculus part 1, g prime of x is equal to f of x, which is just take this function f of t and replace t with x. And we get the square root of 1 plus x squared. So that's really all that's happening with that theorem. To see a little bit more of an advanced example, let's look at this next one. Here, evaluate the derivative with respect to x of the integral from 1 to x to the fourth of secant t dt. This is slightly different than what we just saw in the previous examples. We have a constant for a, and again, a equals 1. It doesn't matter what that constant is. But what is important, instead of x as the upper limit of the integral, we have x to the fourth. This is a composition function. So what this means is that when we're finding the derivative, we're going to have to use the chain rule. Anytime we have a composition of functions, the chain rule is going to come up with the derivative. So to see what happens, we're going to let u equal x to the fourth. So instead of what I had to begin with, the derivative with respect to x of the integral from 1 to x to the fourth of secant t dt, I'm going to replace x to the fourth with u, and I have the derivative with respect to x of the integral from 1 to u of secant t dt. So now, here's where I use the chain rule. Instead of taking the derivative with respect to x, I'm going to take the derivative with respect to u first of that integral from 1 to u of secant t dt, but then I have to multiply by the derivative of u with respect to x. So this is where the chain rule came in. Then by the fundamental theorem of calculus part 1, the derivative of this integral just becomes secant of u, and then I have to now multiply by the derivative of u with respect to x. Secant of u is the same thing as secant of x fourth, just replacing u with x to the fourth again. But then the derivative of u with respect to x, that would be 4 times x to the third. And this becomes our answer. Let's see one more example related to that, and this one actually comes from the homework. Find f prime of x if f of x is equal to the integral from the natural log of x to 13x of e to the t dt. So this is just a step up from the previous example. What I'm going to do is first write f of x by splitting up that integral. This is using another property of integrals that we saw in the previous section. I'm just going to make up a constant that is somewhere between the natural log of x and 13x, because it doesn't matter what that constant is. So if you take a look at the second integral, this one, you can see this is very similar to the one that we just looked at. I've got an integral from a constant to a function. I'm going to have to use the chain rule for that. The first one, though, doesn't quite look the same, but I can switch the limits of integration as long as I use another property of integrals that we saw from the previous section. If I switch the limits of integration, remember that means I have to multiply by a negative to get the opposite. So I'm going to rewrite my function like this. Now let's take the derivative. So f prime of x that would be the derivative with respect to x of the first integral plus the derivative with respect to x of the second integral. And just by noticing what we saw in the previous example, all this really means is you can write the function that is in the integrand evaluated at the function that's the upper limit of the integral, but then multiply by the derivative of that function. That's the upper limit. So this will just become the negative of e to the natural log of x, but then by the chain rule, times the derivative with respect to x of the natural log of x. So you don't have to go through all these steps that I had with replacing it with u. Just remember that that's all you have to do. It's the integrand, e to the t, evaluated at the upper limit, in this case natural log of x, times the derivative with respect to x of that upper limit, natural log of x. So the next integral will be again my integrand, e, but now evaluated at the upper limit, which is 13x, times the derivative with respect to x of 13x. So now let's simplify. Negative e to the negative e to the natural log of x would just be negative x. The derivative with respect to x of natural log of x is 1 over x. And then plus e to the 13x times the derivative with respect to x of 13x, which is 13. So this gives me negative 1 plus 13 e to the 13x. And that's it. Okay, so now let's prove the second part of the fundamental theorem of calculus, which is the most important part and powerful part of this whole theorem, something that we're going to take a lot of advantage of as we even go into calculus 2. The theorem for the second part says, if f is continuous on the closed interval a, b, then the integral from a to b of f of x dx is equal to capital F of a minus capital F of b, where capital F is any antiderivative of lowercase f, meaning from what we learned about antiderivatives, capital F is a function such that capital F prime is equal to lowercase f. So again, let's let g of x be the function that is the integral from a to x of f of t dt. Then by the first part of the fundamental theorem, g prime of x is equal to f of x. So we can see that we're starting to introduce something that involves some of the notation. Thus, lowercase g is an antiderivative of lowercase f. If capital F is any other antiderivative, then we saw before that it will differ from lowercase g by a constant. This means that capital F of x is just the same thing as g of x plus some constant for x between a and b. Also, since f and g are continuous on the closed interval a, b, then the right and left limits at the endpoints a and b also gives us the same result. Capital F of x is equal to g of x plus c. So then, evaluating capital F of b minus capital F of a will just be g of b plus c minus g of a plus c, which the constants will cancel out and just leaves you g of b minus g of a. Then by definition of how we said that g of x was defined, g of b just becomes replacing x with b in the integral minus g of a, which means replacing x with a in the integral. This second integral is just equal to 0, so that leaves us with our result, which is exactly what we wanted to show. What we have here is the integral of the function lowercase f with the limits of integration a to b. It just becomes the difference of the antiderivative evaluated at those endpoints. So to give you an intuitive understanding of why this works, and also why something so simple is so powerful. Remember what we saw about the relationship between velocity and its antiderivative, which is the position function. We saw that the area under the velocity curve is the same as the distance traveled in a time period. We saw that in section 5.1. In other words, the integral from a to b of the velocity function v of t with respect to t will be equal to the position at b, the end, minus s of a, the position at the beginning. So a very powerful result, but also very simple to use. So now just a couple of examples to finish this section. So first, evaluate the integral from -1 to 3 of 1 over x squared dx. And this is a trick question. I just wanted to start with this one just to show you that even though we just learned something, we don't want to be too lazy with it. We do want to think through some of these functions. In a big way, we need to consider, is the function continuous? That is one of the most important parts of the theorems, and it might be something that we gloss over. But we do need continuous functions. So is this function continuous in the interval -1, 3? No. It is undefined at x equals 0. In fact, that's where we get a vertical asymptote. And since we have a vertical asymptote, the function is not continuous. So this is actually a case where the integral doesn't exist. That was something I mentioned a couple of sections ago. And I pointed out that you probably won't see too many questions about integrals that don't exist, mainly because if it doesn't exist, then there's really no sense in talking about it. So this is just kind of a trick question just to make sure that we understand that we do have to be concerned about continuous functions. So now let's move on to an example that is not a trick question. And this also comes from the homework. Evaluate the integral from 1 to 3 of the function -5 x to the 4/3 plus 5 x to the 2/3 dx. So I'm integrating with respect to x. So we need an antiderivative for -5x to the 4/3 plus 5x to the 2/3. So let's just take these piece by piece. How about -5x to the 4/3? Remember with antiderivatives where you have power functions, the constant -5 just carries on through. I have to increase the power by 1, so 4/3 plus 1. But 4/3 plus 1 is the same thing as 4/3 plus 3/3, which just ends up being 7/3. But then I have to divide by the new power. So these are my antiderivatives. Just going to organize my thoughts with these. And then the other one, the constant 5 carries through. And then again, I'm increasing my power by 1. So x to the 2/3 becomes x to the 2/3 plus 3/3, which is 5/3. And then I have to divide by the new power again. So then simplifying the constants that I have, dividing by a fraction is the same thing as multiplying by the reciprocal. -5 times 3 over 7 times x to the 7/3. And then the other one will be 5 times 3/5 times x to the 5/3. So then what I have is -15 over 7 x to the 7/3 and 3 x to the 5/3. So now I've got my antiderivative. So an antiderivative for this function, we can organize a little bit of the notation like this. If f of x was equal to the original function, -5 x to the 4/3 plus 5 x to the 2/3, then the antiderivative, capital F of x, is negative 15 over 7 x to the 7/3 plus 3x to the 5/3. Now, if we wanted to say what's a general antiderivative, then there would be a plus c from what we learned in section 4.9. But for the purposes of the fundamental theorem of calculus part 2, where we are actually evaluating an integral, I want us to keep in mind that in the proof, notice what happened to these constants, capital C. They canceled out. So in the purposes, or for the purposes of using the fundamental theorem of calculus part 2, we actually don't need these general constants. So let's put this all together with our theorem. So by the fundamental theorem of calculus part 2, the integral that we had, which was the integral from 1 to 3 of our function, negative 5x to the 4/3 plus 5x to the 2/3. With respect to x, just becomes capital F of 3, because here b is equal to 3, minus capital F of 1, which means take the function that you just wrote down for capital F and plug in those values of x. Again, you can notice what's about to happen to c if I did include it. I would have a c from f of 3 and a c from f of 1, but I would be subtracting them. They would go away. So this just becomes negative 15 over 7 times 3 to the 7/3 minus, I need to finish my capital F, plus 3 times 3 to the 5/3. Okay, so that's capital F of 3 minus capital F of 1, which will be negative 15 over 7 times 1 to the 7/3 plus 3 times 1 to the 5/3. So if I want to clean this up a little bit, there's not really much that you're going to be able to do, except maybe with the ones that we have over there to the right. So negative 15 over 7 times 3 to the 7/3 plus, this will be 3 times 3 to the 5/3, which there, since I have the same base, I could say that that's 3 to the 8/3. And then subtracting, that gives me plus 15 over 7 times 1 to the 7/3 is just 15 over 7. And then minus 3 times 1 to the 5/3, that's minus 3. And I could combine these terms just by a common denominator. So 15 over 7 minus, that would be 21 over 7. So 15 minus 21 is minus 6 over 7. All right, and I think that's pretty simple enough. So that's our final answer.